I want to walk through one of these questions for you in your lab participation for our Coulomb, Faraday, and Lenz's Law lab. Questions 1 and 2, you will be using this cool FET experiment on the macro scale. I think it's fairly straightforward. You can input the charge quantity on each of our little charged spheres here. You can separate them, and then you can see the magnitude of the electrostatic force between those particles. And I'm asking you to input a couple of different charges and distances in order to see what is the ratio or the difference of the electrostatic force between those objects when you change the charge on the spheres or when you change the distance between the spheres. And then for the third question regarding Coulomb's law, I wanted you to look at Coulomb's law on the atomic scale. So if I go back to my FET experiment and I click atomic scale, here I'm on the atomic scale, the level of like hydrogen and helium atoms, which is how we're going to apply this. So my scale here in distance is in picometers. 1 picometer is 10 to the minus 12 meters. And my charge is quantized in units of the fundamental charge. So if I have one sphere that has a charge of minus 2e, that means it has 2 extra electrons on it. So it's going to have minus 2 times 1.6 times 10 to the minus 19 coulombs on it. If another particle has a charge of plus 4e, that means it has plus 4 times 1.6 times 10 to the minus 19 coulombs, and those would be protons. So if it's positive, electrons if it's negative here. And then I can move the distances between my objects here. I can also see the forces up here. And so what I'm asking you to do is to calculate or use the FET lab to at least find the electrostatic force between the electron and the nucleus of a hydrogen atom, and do the same thing for a helium atom. And that's what you're going to put in these columns here for the electrostatic force between the electron and the nucleus of the hydrogen or the helium atom. So for hydrogen, we're separated 53 picometers. So let me go back here. 53 picometers, so I'll put this one on 0, this other one at around 53, which is about right here. That would be 52, 54, 56, 58, so 53 picometers is right here. And then I'm going to put 1 electron here for Q1, and I've got my nucleus of the hydrogen atom, which has 1 proton, and so that would be plus 1e here. Okay, and then I get the quantity of the electrostatic force between the electron and the nucleus of the hydrogen atom. Here, 8.2 times 10 to the minus 8 newtons. Okay, I'm going to do the same thing, but for a helium atom. Now for helium, we're going to calculate the electrostatic force between one of the electrons in the helium atom, because there's 2 electrons orbiting around the nucleus, and the electrostatic force between one of those electrons and the nucleus of the helium atom. The nucleus of the helium atom has 2 protons and 2 neutrons. So the nucleus of the helium atom has a charge of plus 2e, or plus 2 times the fundamental charge, okay? So my electron minus 1e, my nucleus plus 2e, and in a helium atom, the electron on average is separated from the nucleus by a distance of about 31 picometers. So let me put myself on 31 picometers. So here I get the magnitude of the electrostatic force between my electron and the nucleus of the helium atom. Okay, why are we doing this? So I wanted you to see the magnitude of the electrostatic force between are within the hydrogen and helium atoms, and we're going to compare those to the magnitude of the gravitational force between that orbiting electron and the nucleus of the atom. So we can see, at least on a microscopic scale, how much larger the electrostatic force is compared to the gravitational force. This is not the case on the macroscopic scale, which is the scale of our universe. If we're thinking about the gravitational force between like the Earth and the Moon, it's much, much greater than the electrostatic force between them. So I'm asking you to use the PhET lab here to get the electrostatic force for the hydrogen and helium atoms. And then we are going to look at the gravitational force between the orbiting electron and the nucleus of those atoms. Okay, now the Coulomb's law and the gravitational force law are both examples of inverse square laws. So let me show you that on my board here. Here's our electrostatic force, proportional to 1 over the distance between those objects squared. Gravitational force is also proportional to 1 over the distance between our objects squared. Now, we're getting the electrostatic force from the PhET lab. You're going to calculate the gravitational force here for the hydrogen and the helium atom, and you're going to compare those to our electrostatic force here. So the gravitational force, that's our gravitational constant, which I've given you. And then we've got the mass of one of our objects. That's just going to be the mass of the electron, which I've provided for you. And then we've got the mass of the nucleus. So for a hydrogen atom, the nucleus only contains 1 proton. So this will just be the mass of 1 proton. But for the helium atom, the nucleus of the helium atom has 2 protons and 2 neutrons. So four fundamental particles in that nucleus. And so the mass of the nucleus for our helium atom is going to be bigger than the mass of the nucleus for our hydrogen atom. So you're going to use this to calculate the gravitational force of the hydrogen and the helium atom, remembering that the hydrogen atom has only 1 proton in the middle. The helium atom has 2 protons, 2 neutrons in its nucleus, okay? The R is going to be the same for both of these. And so whenever you compare the ratio of the electrostatic force to the gravitational force, we're going to find that even though they're both really small, many times less than 1, we will find that the electrostatic force is actually 10 to the 39 times larger than the gravitational force. So on these very tiny small scales, on these microscopic scales, on the scales of the smallest things, most fundamental particles in our universe, the electrostatic force is dominating compared to the gravitational force. And when we think about our universe as a whole, the gravitational force between large bodies is always much greater than the electrostatic force between those bodies. And so this is an exercise to compare those.